Thank you for joining in. This project is funded by the European Union Horizon program. Our webinar series Lessons Learned is a part of the Circuits project and contribute to the dissemination of our 3 years innovation action results. Please enjoy.
Please.
Yep, okay. Thank you. So my name is Maarten Bakker from TNO. I will do the presentation together with Corné from TRACXON. And we are working on Pilot 3, and this is about the eco-design and manufacturing of green in-mold electronics. So what are in-mold electronics? This is an advanced manufacturing technique and integrates electronic functionality directly into plastic components. So this is done during the molding process. You see here an example of a coffee machine that we made, which has touch buttons and lighting directly integrated into this panel. So how this is done? This process starts with the normal creation of printed electronic circuits on a flexible substrate. So often on the plastics. And then components are also placed through a pick and place process. So this process up until now is called hybrid printed electronics. That is really a technology that we at TNO specialize in. This film can then be formed into a three-dimensional shape to a thermoforming process and then added to a mold where molten plastic is injected, thereby embedding really the plastic or the electronic functionalities in this plastic component. So this approach of creating electronic products allows us to create more lightweight, compact and fully integrated products. And this technology has many advantages. It is lightweight, compact, and it's fully integrated. So this is really a paradigm shift, but still very innovative and what lower TRL, and it also has some difficulties still to overcome. This is nicely demonstrated here in this figure. Really, what does it mean, this paradigm shift? A big difference compared to conventional electronics with plastics. You see here, for example, on the left, a nice figure that demonstrates in a classic way of producing devices like this, the number of parts that are in there compared to with in-mold electronics, where you have only basically one component. And also, as a result from that, not only that also the weight is decreasing. And this is also especially beneficial for automotive applications, as it helps reduce the weight of the component, and thereby also fuel consumption over the lifetime of the car and CO2 emissions. There is also, like I mentioned, several difficulties. So one trade-off here is that when everything is embedded inside the plastic part, it makes it very hard to do recycling and or repairing of these products because everything is integrated. So one error, one mistake sometimes means already the end of life for this product. So it presents new challenges for end of life management. One concrete example what I want to show you how these devices can reduce greenhouse gas emissions compared to conventional electronics is here an example by TACTOTEC. We're looking here at a gear shift indicator from a car, and they found with an LCA study that there is a 52% reduction of greenhouse gas emissions when you compare it with a conventional product. And interestingly, the most significant factor for this part is actually that there was a great reduction in the size of the required PCB, because many of the components are already integrated into the device itself. So this is, let's say, also the starting point of our circuits pilot. So we thought, hey, how far can we bring this? Instead of not only reducing the size of PCB, can we actually make more complex functionality without having a PCB at all. So completely emitting the PCB and integrating all the components in the plastic. We have done things like that before, but only with very simple functionalities. So only lighting, for example. But for this pilot, we want to see, can we increase the complexity to make it also of more interest for the automotive industry? So that is one of the challenges we set out to explore. So here's then a little bit of an overview of all the things we worked on in our pilot. So the core is a in-mold electronics product, and we worked on several parts of its lifetime, let's say, trying and working on several sustainable aspects for this. So for example, to circle back to one of the other presentations, we also tried to implement different materials such as ultra low temperature solders. And we worked also together with Polyme on the automation of repair and disassembly. One of the main topics I want to show now is just this, indeed, the possibility of disassembly and repair for in-mold electronics. And for that we used a lighting device. So this is a device we already had in-house, and it is one we have characterized very well. And it's really a workhorse for performing beyond state-of-the-art research. So it is a half circular shape. And the composition, as you see here, it is basically almost just plastic. So there's a polycarbonate substrate. It has only some silver circuitry, so only one layer of silver circuitry. So it's quite basic design. And it has 132 LEDs. And then there is, of course, when the device is thermoformed and injection molded with big plastic part. This device still requires, of course, an external PCB for functioning. We use this device in several ways already. So I'll show you some examples here. It is durable, so we have done accelerated lifetime tested on it. And even after we have modified this device based on patented TNO technology that allows us to separate again the injection molded plastic layer from the electric components, let's say. So this allows the device to be disassembled and that the components and the silver can be reached again. So this is new technology that we developed here in-house. And based on this technology, we have shown, for example, you see here that parts can be recycled. So the plastic itself can be recycled. Also, the silver from the circuitry can be retrieved, and the components can also be retrieved. We have also made this device with recycled polycarbonate, which had a content of 90% recycled polycarbonate. Something that we had not done before and that we investigated in this project is if we can also repair broken devices. So instead of disassembly for recycling to all the components, see if we can also repair it. So how does it look like? We have here an example of some mistakes or faults that can happen during the production of these devices. So there is maybe some crack in the circuitry, some components might not work or they might be placed incorrectly. Normally that would mean disregard of the whole device, but in this case we can disassemble through the disassembly layer that we integrated. We have again printed foil basically. It is seen here with the damages again, and we can then repair it and re-injection mold it to a new device. So this is more a schematic of the process. And how does it look like? So here you have an overview, and in green it is a layer on top of the electronics before the injection mold. The plastic is a dismantling layer which allows us to open up the device again. You see here on the left, so we can remove the plastic cover, check the circuitry, check the components, do testing of it, and if needed indeed we can repair it. So that means maybe fixing the circuitry or replacing components. It can then go back into the injection molding device for a new cover. So we have successfully in this project used this approach to restore devices that were not functional to full functionality. We have some downside also on this. For example, that after repair, we sometimes observed maybe a 1, 2 or 3% increase in energy use. That is due to the manual repairing of the circuitry. So now that we have this option for repair, we have more end-of-life scenarios available. And this we compared it with an LCA. So instead of what was already available, disposal, and then having to make a new product, we can now also repair, and then you can incinerate plastic, but also we can repair and recycle the old plastic parts that we took off. So here is a comparison in more detail of all these different end-of-life scenarios that we made. So for our device, and focus on the impact of repair, recycling, and disposal. And there's now 4 main scenarios that we have. So first, there is no repair possible. So we just have to incinerate the whole device and make a new one. Second possibility is we can repair. Third is repair and incinerate the parts that came off from the first one. And the fourth one is we can repair and also recycle the parts that were no longer usable from the first one. And for each of these scenarios, we looked at the materials required, production required, the dismantling steps that required, and also, of course, the time and energy that is then put into this dismantling and repair process. And what happens then to all the different components at the end of life, whether it's incinerated for energy or actually if the materials can be recycled for recovery. Then this is an overview of the results. So there's many intermediate steps, of course, but what you see here is that repair alone provides already a modest reduction in impact on all the different aspects for climate change, let's say. So there's all these different categories are here, and in this case, if it is below 0, then it means it has a negative impact, so it's actually a positive result. And we checked also just for repair and incineration, you see that there is a modest impact, but especially, and that is the other 3 bars or the green bars, that when the components that are no longer used, so the plastic part that was taken off, when it is recycled, then we see a huge impact on actually all the aspects. So all of them are below 0, so that has a very good impact. There are some downsides or still things that we have to work on. For example, there might be a slight quality loss, so a small increase in electricity during use phase. We also already took that into account, so we made analysis where we, let's say, increased the electricity use of the project over its lifetime with 4%. And then, goes down a little bit, but still, it does on the total picture, that does not seem to matter that much. And in some cases, there can be a slight damage of the graphic coating, and this can, of course, sometimes be a problem depending on actually the design of the device. So all in all, this is very positive result. Even in this case, this is still, let's say, pretty much a worst case scenario for repair, because we have only done it on a batch of 4 devices, let's say. So any electricity use for ovens, etc., during repair is split over 4 devices. Of course, maybe in a bigger setting, in industrial production, this is done on more devices, then the electricity use for doing these repair steps per device goes down, of course, and then this becomes even better. Finally, I would like to show you then a new functional demo that we have been working on. And for this, one of the main goals was to demonstrate that we can integrate more complex functionalities directly in mold electronics, because the previous device is just LEDs basically, without using a traditional PCB at all. So this, of course, would then be even more beneficial on LCA. So we, together with the partners, we designed a device, also discussed with automotive what would be the functionalities that that you would like to have included into this. And after several, after 3 years of development, we basically ended up with this demonstrator. So we have a polycarbonate substrate, 3D formed. There's silver circuitry. There are also many LEDs. We have here 2 capacitive touch buttons. We have here capacitive touch sliders. Here on the top, we actually integrated a flexible OLED screen. And here in the middle is a 3D gesture recognition antenna. So you can slide your hands over it, also use the demo. And interestingly, all the components to make this device function are integrated in the device. So there is no PCB required. And all in all, this was a 10+ printed layer design. So for printed electronics, already quite complicated design, let alone making it into a in-mold electronics product. Here you see some of the details of this design, showing amongst others the complexity, the number of silver tracks, the size and the pitch of all these tracks. Also multiple layers, as you can see here, so we have the cross, and the integration of all kind of components and microprocessors. Then I have a small functional demo of this. Of course, this is just a demo, and the lighting looks a little bit strange also due to filming with the camera, but just to show you how it works. So we have some capacitive touch sliders. You see buttons, you can cycle through some things on the screen, different options. And the gesture recognition, just hovering your hand over a device to perform. So that is from TNO side, where we ended up with our demonstrator. Then I give the word to Corné from TRACXON to tell you a little bit about the industrial manufacturing of devices like this. So, Corné.
Yes, thank you. Thank you, Maarten. Perhaps you can go to the next slide. Yes, here we go. So at TRACXON, we worked on, we're a manufacturer, it's a spin-off from Holcenter. We produce printed electronics. And as said during the meeting, it is quite an interesting technology because it's a green technology. Also recycling possibilities are there. But that last is now to geopolitical situation. We can also produce in the Netherlands. We are based in Eindhoven, so one of the most expensive regions in Europe, I would almost say. And then nonetheless, we are able to manufacture and win some of the proposals. So due to our knowledge in printed electronics. So besides the environmental aspect, also the geopolitical aspects of flexible electronics is important. Here you can see our first demo. So the complexity of the second demo was quite high. So as Maarten already said, before getting there, we made a little bit less complex demonstrator, still quite interesting, which is shown in here. And in the next slide, you can also see the details there. Yes. But first, the manufacturing. So printed electronics, hybrid printed electronics is 2 steps. One is a printing, and secondly is a component placing. On the video on the right, you now see how the component placing is going. And on the left, you can see the print. So let's start with the left. When you have a foil, you need to apply conductive circuitry, and we do that through printing. And printing is, especially screen printing, is very beneficial because it puts, let's say, a high amount of metal directly on the web, which provides a lot of current capacity and at the same time a high resolution. Our facilities are an ISO 8 clean room. We print on 60 centimeters web width, and 150, 150 are let's say, TRL7 features that we can easily print. Then on the video on the right, you see the component placing part. Also that we TRACXON has a capacity to do. It's a completely different environment. It's an ESD environment, secured pick and place area, dual head placements, and interconnect dispensing printing. So like was already discussed with Alpha, with low temperature solder, for example, you can apply components and stick them to the foil, which has of course a temperature budget. This machine is also customized for hybrid printed electronics. It includes foil handling and solder reflow. We are able to print also on the 60 centimeter web width about 11,000 components per hour at a 1.8 meter distance. So it is quite fast, and we can do that. Also at TRL7 we do O201 metric, but in this project we have done smaller parts, but those are not, let's say, TRL9. So the challenge now is, of course, to integrate this system into the existing production set. So you need to have the design optimization. The layer stack needs to be optimized. This also includes materials, the formable material, the substrate, the ink, the components, and also the interconnector as discussed. And we need to figure out manufacturing readiness level, MRL, instead of TRL, which is technology readiness level. And manufacturing readiness level involves cost effectiveness, it involves yield, it involves that the machines can be operated with non-skilled people. All these things we took into account. And the next slide. Yeah, you can see the difficulties. Again, in this case, it was not so complicated as the firm's demo, but here you can see that also here chips are integrated into the foil already at the start of the product. In the next slides, you can see that we can manufacture the second version that was shown by Maarten, where we produce on the foil. In this case, you can see the pick and place system that we have used. It's a video, so Maarten, you can start the video. Yeah, I think there's a lot of data missing. So what happens here, the material is scanned, whether the device is flat, whether it's okay. And when it's okay, the machine starts running, and it here places the protective layer of the components. Again, minimize the layers. We went from 9 to 7, increase robustness, make the yield, and do the upscaling tests. And eventually we came out with this product, which is quite nice. We made the product black instead of white in order to show the difference. But also here, the material and devices are upscaled to some extent. We sent them to the partners. We made about 20 pieces of this. Thank you.
Thank you for watching this webinar episode. If you're as passionate about sustainability and innovation as we are, here's how you can get involved. Stay connected with us on our social media and website for the latest updates and insights from the CIR-CUITS project. Whether you're an individual or an organization, there are plenty of ways to contribute. Reach out to us to learn more about partnership opportunities, events, and initiatives.